Okay, then let's give a break to rotations. Now, when we were discussing the Stern-Gerlach experiment at the beginning of the semester, if you remember what we said was, okay, let's assume that we have a oven here which sends some unpolarized beam of silver atoms. Then we had one Stern-Gerlach apparatus here, and the beam, as it went through, it was split into two. One went up, the other went down. And then we said that, okay, so let's block one of them and study the other one. We call that plus state, or we block the top part and we took the bottom part, we call that the minus states. So we basically discussed how we can describe our system after the first Stern-Gerlach apparatus, but not before the first Stern-Gerlach apparatus. How do we describe this unpolarized beam of silver atoms? We never discussed that. Now let's try to describe that unpolarized beam of silver atoms. Now the problem with this unpolarized beam of silver atoms, for example, what does unpolarized mean? When we are doing optics, what's an unpolarized light mean?
Tek bir yöne bağlı olmuyor.
Manyetik alan daha yöne çevrilmiş. Elektrik ve manyetik alana daha yön olarak belirlenmemiş olabilir.
Yani olabiliyor da hep bunların hepsinin bir süperpozisyonu gibi bir şey oluyor.
Yeah. It's just a sum of different ray, and if you are talking about light, it's a sum of different components which points in different directions. Well, the same definition applies here. We have just a collection of silver atoms. Their spin points just in random directions. So if you just take, if you measure the spin of each one of those silver atoms, for example, you will find that 50% is pointing in the plus z direction, 50% is pointing in the minus z direction. Or if you would measure the x component of their spin, not the z, you will find exactly the same thing. 50% will be in the x direction, 50% in the minus x direction, or whichever direction you choose. 50% will be in one direction, 50% will be in the other direction. Well, the immediate guess to describe these unpolarized beam of silver atoms, you can say that, okay, let me describe all of them by some ket alpha. I know that 50% will be in the plus state, 50% will be in the minus z direction. So this will be a possible guess for this unpolarized beam of silver atoms. But this doesn't work. You see, the problem is if you say that this is the beam, I mean, when we are talking about unpolarized beam, whichever Stern-Gerlach apparatus you use, just put some Stern-Gerlach apparatus in whichever direction you choose, it will always split into two. If it's completely unpolarized, it will always be split into two equal parts. But you see, this state that we guessed is nothing but Sx plus state. So if I put a Stern-Gerlach apparatus, which has a magnetic field aligned in the x direction, it will not split my beam into two. Because all of them will just move in the Sx plus direction. None of them will move in the Sx minus direction. Well, you can say, okay, maybe this is a wrong choice for my ket. Let me just choose a ket, let's say with C plus coefficient and C minus coefficient, and let me try to guess what this C plus and C minus coefficients should be. But still, even this ket is some plus ket in some direction n. There is a direction n for which this is an eigen. This will be an eigenstate. whatever this C plus and C minus is. So if you put a Stern-Gerda apparatus which has a magnetic field in that n direction, it will not split my beam into two. So the problem is I cannot describe such an unpolarized beam of silver atoms by a ket. Now what will happen is half of those atoms, let's say, will be in one ket, one will be described with one ket, half of them will be described with some other ket. There won't be a single ket describing my beam of silver atoms. Now, if we are looking for an average of, let's say, some observable, then what we need to do is, well, some of them will be in the ket, let's say, plus. Now, let me write. Whichever direction you like. Not all of them will be in the plus, so when you are taking the average, you also need to take, take into account the fraction of the particles in the plus that can be described by the plus ket. And then some of them will be in the minus ket. Omega plus or minus, the fraction of atoms described by the plus or minus kets. This will be the average for any quantity A. I have a quantum mechanical average, the expectation value, and then I have a statistical average in terms of these omega plus and omega minuses. I have to do both of them at the same time. Well, I can basically do the same thing for any system, not necessarily a Stern-Gerda apparatus. So I can have a given system that can be found, let's say, in the kets AI. If I have some collection of them, the fraction omega I will be in the kets AI. By the way, these AIs need not even be orthogonal. This is not a basis. I'm not choosing a basis. I have an ensemble of particles, just like this beam of particles over here, that I create by some means. And depending on how I create them, some of them will be in the A1 state, some of them will be in the A2 state, some of them will be in the A3 state. It's just an ensemble of particles. I'm considering a state ensemble. And omega I will be just the corresponding weights. So the average of any quantity will be just, well, they can be in the AI state with a weight omega I sum over all the states. This will be my average. So again, I have two kinds of averages. One is the quantum mechanical average, what we call the expectation value, and then the other one is average over these with these weights omega I. Omega I is very similar to our classical probabilities. Now let's see. I will now choose a basis. This is a basis. They are orthonormal. Now this average now becomes omega I, AI, BJ, BJ. This is one. Then I have A. Then I have sum over K, BK, BK. This is again 1 times AI. This is equal to, I have a sum over, let's say, J and K. I'm just moving this sum over J and K outside. I have BJ, A, BK. And then bk ai, well, here I have the sum over I, omega I bk ai ai bj. This is the average of A. Well, you see, I had already defined this quantity as AJK, the matrix element of that operator A in the basis Bj. This is equal to sum over JK, AJK multiplied with omega I bk ai ai bj. Here the sum is over I. Now I will make one more definition. I will call all of this thing rho kj. Now rho kj is equal to sum over I omega I bk ai ai bj. This is equal to bk omega I ai ai bj. You see, this is an operator over here. And I'm taking the kj element of that operator. So basically that operator is what I call the rho. That is the density matrix. And in terms of the density matrix, the average of A is equal to JK, AJK, rho KJ. But you see, this is nothing but a matrix product. If I sum over the K, I get sum over J, A times rho, the JJ element. Now I'm summing over J. JJ element is the diagonal element. So if you sum over the diagonal elements, this is nothing but trace of A times rho. So in a sense, this density matrix specifies all the properties of my system. As in a sense, a generalization of my kets to systems where I cannot really write a single ket for my system. Now let's first see that it works, at least in the case of my spin. Let's see. For my case, the unpolarized beam of silver atoms well, they are in the plus state with 1/2 probability, and they are in the minus state with 1/2 probability. This is the density matrix corresponding to my system. This is nothing but rho is equal to 1/2 times the identity matrix, identity operator. So if you want to calculate, let's say, the expectation value of S dot n, n can be any direction. You can look at the average in the x direction, average in the y direction, average of spin in the z direction. This will be equal to trace of S dot n rho. But rho is just the identity matrix. This is 1/2 trace of Si and I. But the spin, the trace of the spin is just 0. This is 0. So basically this tells me that whatever n is, the probability of having plus in that direction is equal to the probability of having minus in the same direction. Whatever n is. You see, we are here. Here. Not really. Let's do, I mean, this is what we want to have. The average of spin in any direction should be 0 for an unpolarized beam, because in that direction, the probability of pointing in that direction is the same as the probability of pointing in the opposite direction. This is what we want. Now, let's look at S dot x hat in my state. Well, let me write it this way. You see, initially, I said, sorry. Our guess was this one, 1 over square root of 2 plus minus. Plus minus 1 over square root of 2. Let's look at this one for our initial guess, which turned out not to be correct. Well, if you calculate this, this just turns out to be h bar over 2. Non-zero. So the average of Sx in such a ket is not 0. But what we want is the average of Sx should be always, I mean, whatever the direction is, the average of S dot n should be 0 in an unpolarized beam. There is no preferred polarization direction. Yes, your question. So what do we want? We want to describe a system which doesn't have any polarization. It's unpolarized. Meaning that if you calculate this, the average of spin in any direction, it should be 0. That is what we want. At the beginning we said, okay, considering what we know up to this point, the first guess would be this one. Well, it is 50% in the SZ plus direction, 50% in the SZ minus direction. Right? That was our first guess. Let's describe this unpolarized beam of particles with this ket. But if we consider such a ket, we see that the average of Sx for this system is not 0. What we want is the average of spin, whichever direction it is, it should always be 0 in an unpolarized beam. There is no preferred polarization direction. So from here we conclude that we cannot use kets to describe a system of unpolarized particles. There is no single ket describing such a system. So we are kind of generalizing our description. We are saying that, okay, for such a system we will not be using the kets or the wave functions. We will be using density matrix. And for this density matrix, we had seen that at least in the simple case, we started by such a density matrix. We said that this density matrix satisfies our expectation that the average of the spin in any direction is always 0 for a system described by this density matrix. Sure.
Yani ben o zaman şey düşünüyorum, sistemde aslında hani %50 up, %50 down olduğu için sıfırlamıyorum. Henüz öyle bir ölçüm yapılmadı. Sistemde hani zorunlu bir spin state yok.
Okay.
Bunu dediğim zaman tamam ya, o zaman density dediğimiz şey ne?
Now, you see, what is my observation? I put my system in a Stern-Gerlach experiment. So, okay, there is no measurement yet, but somehow I want to describe it. So what you do if you want to describe a system, you make measurements on that system, you take results of your measurements, and then from those results you try to construct what the system was before your measurement. Well, you see, there is no eigenket describing my system before, but there is a ket describing my system even before the measurement. You see, if you take a single electron, I might not be able to talk about its spin in the x direction. That is because it can be a superposition of kets with different components in the, you see, if you look at this, a single electron, its state can be described by this system. Even before the measurement, I can say that my electron is described by a ket, and that ket will have this form. I don't know whether it has SZ plus or SZ minus. It doesn't have any one of them, in fact, before measurement, as you said. But still, it has a ket before the measurement. There is a ket describing my electron. Once, and then if I had known this ket, I can then say, if I make a measurement of the spin in the z direction, with what probability I will get plus h bar over 2, with what probability I will get a minus h bar over 2, if I knew this ket. So what we do, we just create many copies, identical copies of my system, and I make measurements on these identical copies. I make different measurements. I measure I take some group of them and measure their spin in the x direction. That will give me the magnitudes of A and B. I will take another group, and for this other group, I will measure the spin in the, let's say, x direction, not the z direction, and those measurements will give me what is the relative phase between A and B. And then from this knowledge, I know I can determine what the initial ket was. This system doesn't have a definite z component of the spin, but nevertheless it still has a ket.
Ama bunu söylediğiniz zaman spin herhangi bir klasik özellikten bir farkı kalmıyor. Yani spinle mes arasında hiçbir fark yok şu an bu yazdığınızda.
Why?
Çünkü ben ölçmesem bile bir spin değeri vardır diyorum.
Ama no. This state does not have a spin value yet along the z direction.
Ama spin gibi bir özelliği olmasına rağmen ben tüm spinleri çıkardım.
No, hold on. We are not saying that the spin property doesn't exist. The spin property does exist. It just doesn't have a specific value. It doesn't have a particular value. I can still talk about the spin wave function, but I cannot talk about the value of the spin. That is what we mean when we say that the spin doesn't exist. The electron, whether we measure it or not, is always a spin 1/2 particle. When we say an electron, we are already specifying it. When we are measuring that and determining that that particle is an electron, at that moment we know that it's a spin 1/2 particle. And at that moment we are saying that its ket can be written in this form. It's just its spin in the z direction doesn't have a specific value.
Bu durumda da o zaman yine %100 bölüştüğünü kabul etmemiz gerekiyor.
Not necessarily, depends on how you prepare it. Maybe it's 50% to 50%, maybe it's 80% to 20%, we don't know.
Ama yeterince beklersek herhalde %100% olacak.
Why?
Sürekli değişmeyecek. Yani bu süper.
Why should it change? You see, what you are saying is its value will change. Well, of course, if you have a time evolution in the system, of course it will change, but let's say that we are looking at my system at a particular time, so there is no time evolution. So this doesn't tell me that the spin of the electron is constantly changing from plus to minus. There is no such change. It just doesn't have a value before we make a measurement.
Peki. O zaman measurem'dan önce bu kadar belirsizken biz, yani sistem varsa elimizde density'yi nasıl tanımlıyoruz? Gözlem yaptığımız zaman yani fiziksel olarak nasıl çıkarıyoruz?
We will see. You see, for example, this density matrix is most of the time used in statistical physics. That is where we will be using, because, you see, if you don't know how you created your system, there is no way you can tell what the spin will be or what the density matrix will be. But here what I am saying, for example, in this experiment, I am saying that it is completely unpolarized. That specification already tells me what the density matrix is. How do I know that it is completely unpolarized? That's another question. But assuming that I know it is completely unpolarized, is how do you create unpolarized beam? You heat it. Temperature has this tendency to wipe up any information. So no information is left. No information about any direction is left. So the beam, you think that it is completely unpolarized. Then of course you can say that, how do we know that? Well, you create your system, let's say, you have your oven, you heat it up. From the oven comes out the silver atoms. You have a Stern-Gerda apparatus somewhere else. You measure how the beam is split. Let's say you have a setup in which you can change the direction of the magnetic field. And if you change, as you change the direction of the magnetic field, the beam just, whatever the direction, the beam splits into two equal parts. If you measure that, then you know that this oven creates an unpolarized beam of silver atoms. And then it's kind of an assumption, assuming that you work the machine with the same properties in some other place, it will create a beam of silver atoms with the same properties. That's kind of one of the fundamental assumptions of doing, let's say, science. So we assume that identical conditions creates identical systems. Then we know that once we make one measurement, we know that this oven creates a beam of unpolarized silver atoms. It might happen that when you take this oven, you go to a calibration laboratory, they make this measurement, and what they find is, okay, if it is aligned, let's say, in the Z direction, it is 50-50, but when you align it in the X direction, it is 60-40. Then such a beam is not completely unpolarized. It is partially polarized. And from that information, how the splitting changes depending on the alignment of your magnetic field, you can determine whether what are its polarization properties. Let's see. I didn't yet show that it has this form. But what I have shown here is that for a system described by this density matrix, the expectation value of spin is 0, whatever the direction of spin is. So let's try to write this in a different basis, let's say. Here I use SZ basis, SZ plus minus basis. But I can just do the same thing with Sx plus or minus basis. Let's see. This rho is equal to 1/2 plus minus minus. Well, I also know that this plus basis, plus ket, is 1/2 square root of 2 Sx plus Sx minus. And minus is 1/square root of 2 Sx plus minus Sx minus. Do you agree? Let's look at this operator. I either take the lower sign on both sides or the upper sign on both sides. This is equal to 1/2 Sx plus or minus Sx minus times Sx plus or minus Sx minus. Nope, this is the other way around. Let me just multiply them up. I will have 1/2 Sx plus Sx plus Sx plus Sx minus Sx minus plus or minus 1/2 Sx plus Sx minus plus Sx minus Sx plus. So when I look at plus minus, plus minus minus. This is my row. I just take this term with the lower sign, add to it the same term with the upper sign. The first laws, they just add up. So I end up having Sx plus plus Sx minus 1/2. This is the first line. The sum of the first line, the sum of the second lines, they just give 0. So you see, the same system, I can either say that 50% is Sz plus 50% Sz minus, or 50% Sx plus 50% Sx minus. They are the same thing. Well, you can do the same thing for the y component also, or the any n direction. So whatever spin direction you prefer to use, the density matrix is always 1/2 times the identity operator. So that is what we wanted, right? So we wanted the whatever the n component is, our ensemble of particles is 50% plus in that direction, 50% minus in that direction.
Benim aklıma şey geliyor. Biz bunu ansör pratiğiyle yaptığımızda diyorduk ki işte S'nin beklenen değerini ve beklenen değerinin karesini S'nin ketleriyle yaptığımızda tamam sıfır bekliyorduk. Burada o zaman onu 3 boyutlu duruma generalize mi ediyoruz? Yani density of metric.
You see, what we are doing over here is we are looking, the first claim I made is that if I have a system of particles, not just a single particle, I cannot describe my system of particles as a single ket. That is the first thing I say. So our description up to this point, in terms of the kets and the wave functions, etc., it doesn't work for systems of particles. So we need something else to describe this system of particles. And that something else is what we call this density matrix. This is kind of a generalization. But of course, if this is a generalization, whatever we did before, we should be able to do it with the density matrix. Well, that's kind of easy. Okay, I know that I cannot describe every system by a ket, but let's say we take a system which is described by a ket. Well, with 100% probability, my particle is in this state, right? So my density matrix is just 1 psi psi. Does it work with expectation values? This is how we had defined it before the expectation value. Now this I can write as sum over, let's say, a j psi bj a psi, which is sum over j bj a psi psi bj. Sum over j bj a times psi psi, sum over j bj a times rho, sum over j a times rho, the jj element, trace of a times rho. So if I have a system in which all the particles can be described by a single ket, I just recover my previous derivative results.
Son bir şey soracağım. İstatistiksel probability eklememizin burada hani ne katkısı oluyor başta? Yani zaten bize yine product arasındaki observable şeyi vermiyor mu? Probability vermiyor mu?
You see, it's not about probabilities. The question is, how can we describe this system? Then, of course, we eventually, once we decide on how we describe our system, then we can talk about probabilities, etc. But the question is how to describe a system. So before we were talking about kits. You said that, okay, for such and such particles we can describe the system using kits. As a specific example, we looked at the beams after they split in a Stern-Gerlach experiment. We just blocked one of the beams, we kept the other one. We said that, okay, all these particles over there, they have a definite kit. But not all systems can be described by a definite kit. That is the claim. Then the question is, how do we describe it if we cannot use a kit notation? Now there kind of enters into the game the classical probabilities. When we are talking about the expectation values, this time, okay, I have this collection of particles. Some of them will be described by these kits, let's say AI. For those states, the expectation value of A is this one, but not all of them are described by these kits AI. Some of them are described by some other AIs. So you just multiply them. What do you mean by the average? If you make many measurements, what you will obtain? Let's say you have 1, 2, 3 Ni particles, N1 particles in the state A1, N1 plus 1, N1 plus N2, and 2 particles in the state A2. Okay? So if you want to calculate the average of A, you just take the expectation value in the first state. There are N1 of them. Of course, some of them will be, so let's just multiply this by N1. If you just calculate the outcomes of the A measurement, in all, well, the average of A, you can say that is you just make measurements on each one of them. You just sum the outcomes, divide by the number of measurements you made. So I make N1 measurements on particles that are in the kit A1. The average for this kit A1 of the operator A is this matrix element over here. That's the average. If I multiply it by N1, that will give me the total of the A measurements on that N1 particles. Then I make the measurement on the other particles. This is the sum of the A outcomes in all my measurements. Then I need to divide by N1 plus N2 if I have a mixture of these kits. Omega 1 is what I call N1 over N1 plus N2. This is the probability that if I pick a random particle, it will be described by the kit A1. And then I have omega 2, which is N2 over N1 plus N2. Again, this is the probability or the weight, whichever one you prefer, that if you pick a random particle, it will be described by the kit A2. So we are kind of making two averages. One average, quantum mechanical average. The second average is the kind of the classical average, the weight average. So now the average of A just becomes omega 1, A1, A1, plus omega 2, A2, A2. So for this system of particles, I cannot write a single kit. Some of them are described by one kit, some of them are described by the other kit. For example, how you create them. Let's say you take a beam of silver atoms, two beams of silver atoms. You send one of them through a Stern-Gerlach apparatus aligned in the x direction, and you choose x plus component. You take the other beam, and you let it pass through another Stern-Gerlach experiment that's with a magnetic field aligned in the z direction. You choose the z plus. You send the beam, it splits into two. Let's say you block this one. You take a beam, you send it through a Stern-Gerlach in the z direction. You block, let's say, this one. So you have one beam, you have another beam, and then you just mix those beams. This is one way of creating some partially polarized, let's say, mixture of silver atoms. You are just mixing them. Of course, you can adjust how many S6 plus silver atoms you take, how many S8 plus silver atoms you take, etc. And that gives you the weights. In the final beam, let's say you send, when you send 5 units from the top and then 10 units from the bottom, your density matrix will be just 5 over 15 S6 plus S6 plus 10 over 15 SZ plus SZ plus. This will be your density matrix. It depends on how you create your system. And you see, keep in mind, this is an example where S6 plus and SZ plus, they're not orthogonal to each other. They don't have to be orthogonal to each other.
Peki en son karışık halinde ölçüm yaptığım zaman S6 plus bulma olasılığı ne mesela?
Well, I can write this as, let's say, A1 S6 plus B1 S6 plus S6 minus S6 minus. Just write SZ plus as plus C1 plus D1 B1 is the probability that you are looking for. Sure. I mean, you see, you can always write SZ plus in terms of S6 plus and S6 minus. And once you write SZ plus in terms of S6 plus and SZ minus, just like we did over here, well, the thing is, you also get these terms, these additional terms, non-diagonal terms in your density matrix. But the probability that you are looking for is this one. You see, basically, for a given kit, state alpha, let's say, the probability that it is in a, let's say, S6 plus is this one. This is equal to alpha, no, S6 plus alpha S6 plus. This was our notation in the kit case. This I can write as trace of alpha S6 plus This is, well, in our new notation, this is trace of row Sx plus Sx plus. This will be true even for systems in which you cannot describe it as a single ket alpha. Just put here whatever the density matrix is describing your system. This is the probability of Sx plus. And that will be basically this diagonal element over here, B1. Okay, I need to go to my other lecture, so we can continue on Wednesday.